Hi, hello students, good evening everyone. I hope all are doing well. Anyway, warm welcome all of you to the Infinity Learn JEE YouTube channel. This is me Surya, your chemistry faculty from Infinity Learn. Okay, I hope I am perfectly audible and visible to each and everyone present over here. Okay, today we are going to the next part of our same chapter, that is the thermodynamics. We will be talking about the energy, work and heat detailing in this particular session. Okay, right? Okay, now let us start with what we mean by energy, right? We need energy, right? To do some work, we need more energy. So, we can define energy as the ability, right? Or the capacity to do work. The capacity to do work is known as the energy, right? Yes. So, energy can be defined as the capacity to do work or the property that is absorbed, that is obtained, right? The property that is obtained through work or that can be converted into work, that is known as the energy, right? So we can define that energy means the ability to do work. So in terms of chemistry or in terms of thermodynamics, we will be defining about the energy as in terms of internal energy, right? I hope all of you have the idea about the internal energy. So what do you mean by internal energy? Okay, in chemistry point of view or in thermodynamics view, we can define the internal energy as the energy stored in a substance, right? Energy stored in a substance is known as the internal energy, or it can be denoted by the letter capital E or U, right? Capital E or U, that is known as the internal energy. Otherwise, we can define as it is a sum of energy, sum of all forms of energy that is present in a substance, right? Which is including kinetic energy, right? This is due to the formation of or by the movement, right? Yeah, that is during vibration or something. So we can say that the kinetic energy is present in a substance. Similarly, potential energy is also present, right? Potential energy is also present there. So we can say that the internal energy of a system is the sum of all forms of energy, including potential energy and kinetic energy. Then there is one exception that whenever we are discussing about the gravitational field, right, there will be gravitational energy. So whenever we are discussing about the internal energy, it can be excluded that it is a sum of all forms of energy other than gravitational energy. Other than gravitational energy is known as the internal energy. Right. Now, whenever we are doing any calculations, it should be, the unit of internal energy should be given in kilojoule per mole, right? Kilojoule per mole. Generally, kilojoule is the energy of, unit of the energy, and per mole, which is the unit of internal energy, right? Clear? Now, let us discuss about the change in internal energy, right? Change in internal energy. How the internal energy can be changed, whether we are doing work or by changing heat, right? So we can say that we can change the internal energy of a system either by doing work or either by changing heat, right? By transfer of heat. So I can define the heat as Q, right? I'm just explaining or denoting the heat as small letter q. So I can say that by transfer of heat, internal energy changes. So if the heat is absorbing, right, if the heat is absorbing, we can say that q is equal to positive for absorption of heat, right? Then what about the sign of q whenever I am taking the heat, whenever there is a release of heat, right? Whenever the heat is releasing, it will be negative, right? Heat is releasing, so I can say that q will be negative. Whether it is absorbing, it will be positive. If it is releasing, it will be negative. So this will be the two Adiabatic convention or the sign of heat while absorption of heat as well as release of heat. Similarly, we can change the internal energy by doing work also. We have already studied about the system and surroundings, right? So we can say that if the work is done by the system, right? Work is done by the system. System is already there and surrounding is also there. So if the work is done by the system, we can say that the sign of W will be negative, right? Sign of W will be negative. These sign conventions should be very important whenever we are discussing about the numerical problems, right? Then if the work is done on the system by the surrounding, right? Work is done on the system by the surrounding, it can taken as positive. Right. So this is the basics of first law of thermodynamics. The first law of thermodynamics can be explained by the term internal energy that this is the change in internal energy, right? So internal energy can be changed by either transfer of heat, right? Either transfer of heat, I'm denoting by Q, or either by doing work, right? By the system or on the system. So this will be the mathematical expression of first law of thermodynamics, that delta U is equal to Q plus W, where delta U is the change in internal energy, Q is the heat absorbed or released. Depending upon the absorption or releasing, it will be taken as positive or negative, right? Then W will be the work done by the system or done on the system. This is the basics of first law of thermodynamics. Now we will be discussing about the important terms, right? Heat and work, right? We will be starting with the heat term. What do you mean by heat? It is related to temperature, right? Similarly, heat is also a form of energy. So it can be defined as the energy which is transferred from one body to another body depending upon their change in temperature, right? Depending upon their change in temperature, the energy that is transferred from one body to another is known as the heat energy, right? Heat energy. So I can say that whenever I am taking any system here, right? This will be the system in T1 temperature. This will be the system in or another substance in temperature T2, right? If I am saying that if T1 is greater than T2, right? T1 is greater than T2, what will happen to the heat? Whether heat is going out from the first one or absorbing from the first one, what will happen? If T1 is greater than T2. Heat is going from cold temperature, right? Okay. Heat is going here from T1 to T2, which means hot body to cold body or high temperature to low temperature. Heat is always going from high temperature to low temperature. This will be the high temperature T1. Then the second one is the low temperature T2. Right. That's already written here. The energy which is transferred from one body to another which differ in their temperature. For example, from hot body to cold body, that is having the high temperature to low temperature, it will transfer the heat, right? That form of energy is known as the heat. Clear? Again, heat is measured in terms of calories or joules. Unit is given as calories or joules. We may have the questions in whether it is in joules, kilojoules or calories. Now, another important term that connected with the thermodynamics is that heat capacity, right? Heat capacity. It can be defined as the heat that is required to raise the temperature, of the system by 1 degree centigrade or 1 degree Celsius or by 1 Kelvin, right? If I am changing the temperature of a system by 1 degree Celsius or 1 Kelvin, how much amount of energy I am giving, right? I am giving to the system. That will be the capacity of that particular system. So it can be defined as the heat capacity. It can be defined as the heat capacity and it is denoted by the letter capital C. So, for example, if I am taking a system at 43 degrees centigrade, right? A system at 43 degrees centigrade, and I am saying that if it is changing to 45 degrees centigrade, right? 45 centigrade, it will taking about 2000, right? 2000 joule of energy, 2000 joule of energy, right? If a system at 43 degrees centigrade or degrees Celsius is changing from 43 to 45 degrees centigrade, it is taking a heat of around 2000 joule, right? 2000 joule. So, what will be the heat capacity? What will be the heat capacity? (43 degrees centigrade to 45 degrees centigrade means 2 centigrade, right? It is changing around 2 centigrade. So, I can say that our heat capacity definition is that whenever the heat is absorbing by change the system, to change the temperature by 1 degree centigrade or 1 Kelvin. So, if I am taking here 2 degrees centigrade, I can say that the heat capacity is equal to 2000 by 2, right? 2000 by 2. This 2000 means heat, right? Heat absorbed or heat given to the system, 2000, and this 2 means change in temperature, right? 45 minus 43, that is equal to 2, which means change in temperature. So, we can define the formula for heat capacity as C is equal to Q by delta T, where Q is the heat given, then delta T is the change in temperature. Delta T is the change in temperature. Clear? That will be the formula to calculate the heat capacity of a system if heat is given as Q and the change in temperature is also given. Right? Now, again, the heat capacity can be divided into two types. That is heat capacity at constant volume, denoted by the CV letter. Capital C is denoted by the heat capacity. If it is taken at the constant volume, we can call it as CV, right? We can call it as CV. Then what about the second one? It is the heat capacity taken at constant pressure. So, it is defined as, or it is denoted by the letter CP. P stands for pressure and C stands for the heat capacity. Clear? Yes. Yesterday in the previous session we have studied about the state functions, right? State functions means that depends on the state, not on the path, right? Depends on the state, not on the path. So again we can say that these heat capacities, right, depends on state only, not on path. So we can define these heat capacity Cp and Cv as the state functions. So we can find out the value from initial state as well as final state. So the very important point you have to be noted about the heat capacity is that the heat capacity at constant volume can be defined as the change in internal energy. Change in internal energy of the system. Change in internal energy of the system. The change in internal energy of the system at constant temperature, right? At constant temperature. Otherwise, it is defined as dou E by dou T, right? This is a differentiation in the terms of constant volume. Then what about the second one? The heat capacity at constant pressure, right? Heat capacity at constant pressure. Cp is equal to heat capacity at constant pressure. Cp is defined as the change in enthalpy, dou H, right? Change in enthalpy of the system at constant temperature. So dou H by dou T at constant pressure. Clear? Okay, these are the important terms that are connected to the heat capacity. There are two types of heat capacity. One is at the constant volume denoted by Cv, and second one is at the constant pressure denoted by Cp. Then Cp and Cv are again connected by internal energy as well as enthalpy. Cv is equal to the change in internal energy at constant temperature, and Cp is equal to the change in enthalpy at constant temperature. Clear? Now, the next relation you have to be derived from Cp and Cv, that is the Mayer's relation. Before that, you have an idea about what you mean by enthalpy, right? What you mean by enthalpy? Something related to energy. So, again, this enthalpy can be derived as the sum of internal energy, right? Sum of internal energy of a system and the work form of energy. Work form of energy of the system is called the enthalpy, right? From the mathematical expression, you can see that H denotes the enthalpy, and that is equal to the sum of internal energy. Internal energy can be denoted as either E or U, right? E or U. So, it is equal to enthalpy H is equal to E plus PV, where PV is the work done, right? You will be discussing detail about the work done, that is the pressure volume work. So, PV is equal to the work done. Right, therefore, the mathematical expression for finding enthalpy is equal to the sum of internal energy, E plus work done. Work done is equal to P into V, that is pressure into volume. So, then one more important term you have to be denoted that while doing the numerical problems, this formula is very important, right? I hope everyone aware about the ideal gas equation, right? Ideal gas equation, PV is equal to nRT. Whenever there is a change in volume, right, P delta V is equal to delta Ng into RT. So we can define the P delta V is equal to delta Ng RT, where delta Ng is equal to the change in number of moles of gaseous products and gaseous reactants, right? All the products and reactants should be in gaseous form. So that we can define this equation again into delta H is equal to delta U plus delta Ng RT, where delta U is the change in internal energy, right? Change in internal energy. then this PV work or pressure volume work can be divided into delta NGRT. So the final formula will become delta H is equal to delta U plus delta NGRT. Clear? Now, depending upon the sign of enthalpy, we can define as two different processes, right? Two different processes. The first one is the endothermic process and second one is the exothermic process. Okay, exothermic means heat is releasing, right? Heat is releasing. So we can define as enthalpy is equal to here. It is negative sign, right? Enthalpy will be negative. So delta H is negative for exothermic reactions which involve heat during the process, right? Which involve heat during the process. So the next one is the endothermic process, right? Endothermic process. In the case of endothermic process, we will define as delta H is equal to positive, right? Delta H is equal to positive, which means that heat is absorbing. Heat is absorbing from the system. Heat is absorbing by the system from the surroundings, right? Heat is absorb heat from the surroundings by the system. So we can take it as an endothermic process where delta H is equal to positive. Clear? Now this is the important relation that we have to be derived, that is known as the Mayer's relation, that is the relationship between Cp and Cv, that is equal to Mayer's relation. Okay, we have studied about the formula or expression for the enthalpy, right? So whenever we are considering about the ideal gases, we can say that delta H is equal to E plus PV, right? Where E is the internal energy and PV is the pressure volume work. So whenever I am differentiating this with respect to temperature, I can say it as dH by dt, right? Differentiating enthalpy with respect to temperature, that is dH by dt. Similarly, we are differentiating these terms also with respect to temperature. It will term as dE by dt plus d by dt of PV, right? D by dt of PV. Now we are applying the ideal gas equation here. Ideal gas equation here. Ideal gas equation means PV is equal to nRT, right? If we are considering number of moles is equal to 1 mole, we can term it is as PV is equal to RT, right? PV is equal to RT. So we will be changing here. This PV is changed to RT. So it will become dH by dt is equal to d by dt. Same term, right? d by dt plus d by dt of RT here. D by dt of RT here. Then R is already a constant, right? This is the gas constant. Universal gas constant R. So this is a constant term. So I am taking out from the bracket here. So it will become dH by dt is equal to d by dt plus R into dt by dt, which will become 1, right? Which will become 1. So I can say it as dH by dt minus d by dt is equal to R, right? Clear? dH by dt minus d by dt is equal to R. Hi Satyam, good evening. So we have already discussed about the Cp and Cv, right? Cp means that heat capacity at constant pressure, it is defined as the enthalpy, right? Change in enthalpy. So I will written it as Cp minus Cv. This term will become Cp and this term will become Cv. So I can written it as Cp minus Cv is equal to R. This will be our final Mayer's relation. This will be our final Mayer's relation. Clear? Okay, this first step we are going to do the enthalpy expression, right? H is equal to E plus PV. Now we are differentiating that each term with respect to temperature. So you will get the term around dH by dt is equal to d by dt plus d of PV by dt. Then this PV term is connected with the ideal gas equation. It will term it as RT, right? While solving this equation, you will get the final answer is around dH by dt minus dE by dt is equal to R. Whenever we are discussing about the heat capacities at constant volume and temperature, we have studied that the constant heat capacity at constant pressure is equal to the change in enthalpy and heat capacity at constant volume is equal to the change in internal energy, right? So we can term it as Cp minus Cv is equal to R, where R is the universal gas constant. This will be our final Mayer's relation. Clear? Okay, so far we discussed about the energy term, right? Energy is the capacity to do work. So we have studied that. We have studied in terms of thermodynamics, there is the internal energy, which will be equal to the sum of kinetic energy as well as potential energy, which is present on the system. So we will be discussing about the heat capacity, right? We can change that. Internal energy of a system can be changed by doing work or changing the heat. The first time we have discussed about the heat. Now we will be going to discuss about what you mean by work, what will be the different processes or work done during different processes, right? So again, I have already mentioned in the first slide, it is that the work is taken as positive, right? Work is taken as positive if the work is done on the system. If the work is done on the system, it will be taken as positive, right? Then just opposite that, if the work is done by the system, if the work is done by the system by itself, it will be taken as negative, right? This is the IUPAC convention or the sign convention in which W is taken as positive or negative. Depending upon the condition, you will be calculating the numerical problems, right? Whether work is positive or work is negative. Now, what is the general expression for the work, right? What will be the general expression for the work? In physics terms, you will be studying about work will be the force into displacement, right? Work will be force into displacement. So here we will be discussing the work in terms of pressure and volume, right? Pressure and volume. So if I am giving an external pressure to a system, right? If I am giving an external pressure to a system, I can denote that this external pressure as P external, right? P external. Then due to this external pressure, volume will be changing, right? Volume will be changing. So the final work done will be equal to the P external into delta V, where you will get the negative sign, right? Negative sign. Therefore, work done is equal to, general expression for work done is equal to minus of P external into delta V, where P external is the pressure that is given by externally, right? Given externally. Then delta V is the change in volume. So we can define this delta V as Vf minus Vi. Vf means final volume and Vi means initial volume. Clear? Now let us see about what will happen to the work done during expansion as well as compression work, right? Expansion as well as compression work. For example, if I am taking a container, right? If I am taking a container here, then if this container is containing any gas, right? Let's assume this will be a gas. So, now I am keeping a piston over here. I can say that in a container a gas is present over here. Now I am placing a piston over here. Then if I am saying that like that, okay, this is the, okay, this gas is exerting a pressure towards the upside, right? So this will be termed as P of gas, pressure of gas. Similarly, this piston is also providing a pressure, right? Piston is also providing a pressure out here. So I can say that this is the external pressure, right? This will be the external pressure I am providing by using a piston here. So this will be the external pressure, P external, right? External pressure or P external. For example, for the first condition, if I am saying P gas is greater than P external, right? P gas is greater than P external. What will happen to the volume? P gas is greater than P external, which means that pressure is exerting more, gas is exerting more pressure, right? Gas is exerting more pressure on the system. So I can say that volume is increases, right? Volume is increases. Volume is increases, right? Towards the beginning, volume will be very small. Towards then, it will increases, which means that change in volume will be positive, right? Change in volume will be positive, or I can say that this will be the expansion work, right? Expansion work. This will be the process of expansion or expansion work. So, generally, they have an expression, right? Minus of P external into delta V. What will be the sign of work whenever we are doing the expansion? Whenever we are doing the expansion, what will be the sign of work? Whether it is positive or negative. Negative, right? Already volume is increasing, which means that delta V is positive here. So this term will be positive. Negative into positive, it will be negative, right? So work is done here is negative. Or otherwise you can remind this term as whenever you are doing any expansion work, right? Whenever you are doing any expansion work, the sign of this expansion work will be negative, right? Sign of this expansion work will be negative. Or you can say that the pressure is exerted by the gas, right? Which means that this work is done by the system, right? Work is done by the system. So, in terms of expansion also, you can define the sign of work as work done by the system is equal to negative. Work done by the system is equal to negative. Clear? Then what will be the next condition if you are considering the compression work here? Similarly, I am taking the same container, right? Same container here. Again, a gas is present over this particular container. Same, the piston is also present here. The first one will be the pressure exerted by the gas, right? Pressure exerted by the gas. That is P of gas. Then, if the piston is exerting pressure here, it will be taken as P external, right? P external. So the next condition it is that P of gas, pressure exerted by the gas is less than P external, right? Just opposite condition to the expansion work. Pressure of gas less than P external, or we can say that P external is greater than P gas, right? Which means the piston is moving down here. It is compressing, right? Volume is decreasing here. It is compressing. Volume decreases here, which means this is a compression work, right? This means it is a compression work, or we can say that change in volume will be negative, right? Change in volume will be negative. This will be the compression work. So in general terms, W is equal to minus of P external into delta V, right? Minus of P external into delta V. Here already delta V, change in volume is negative, right? Change in volume is negative. So final term of work is equal to negative into negative, that will be positive, right? That will be positive. So we can say that the work done during a compression, right? During a compression work, it will be positive. Otherwise, we can say that, okay, here, right? P external is right. P external is greater, right? Which means that work is done on the system by this piston, right? Work is done on the system by this piston. Or it will be the compression work, that is equal to the sign of this particular work is equal to positive. Clear? Okay, depending upon the process, two types of works are there. First one is the expansion work, which means that external pressure is small, right? External pressure is very low. So we can say that it is expanding, which means volume is increases. Volume is increases, so that work will equal to negative in terms. Otherwise, we can say that if the work is done by the system, it will be taken as negative. Similarly, in the case of compression work, whenever we are doing compression, volume is decreasing, right? Whenever volume decreasing, delta V become negative, right? Delta V become negative. So the final term W is equal to positive here, which means that during compression work is done on the system. So we can define the sign of work during expansion as well as compression work. Now the next term or next process we have to be discussed about the free expansion. What will be the work done during free expansion? Free, right? Free means vacuum. Here we are considering the expansion of a gas into vacuum, which means the external pressure, right? P external, the external pressure will be 0. That is the vacuum condition, right? So whenever we are taking an expansion of a gas at vacuum, or P external is equal to 0, right? P external is equal to 0. Then what about the general expression for the work? Minus P external into delta V, right? Minus P external into delta V, that is equal to, already P external is equal to 0 for a free expansion or the vacuum, right? So it will become 0. So we can say that whenever there is a free expansion happening during the vacuum, there is no work done, which means work done is equal to 0. No work is done during the free expansion of an ideal gas, whether the process is reversible or irreversible. In the previous session, we have discussed about the two types of process, right? Reversible as well as irreversible process. Whenever we are taking any of the ideal gas, right? Any of the gas or ideal gas, during the free expansion towards the vacuum, the value of work will be 0, whether it is reversible or irreversible process. Clear? That is the condition for a free expansion work. Now let us discuss about the work done during an reversible as well as irreversible process. We will be starting with the reversible process, right? Reversible process. Reversible process means the process which is happening, which can be reversed back, right? Which can be reversed back. So, if the compression is occurs in large number of series or the steps, right? Large number of series or the steps, we will term these process as reversible process, such that the volume changes by a small amount. Such that in the case of a reversible process, the volume is always changes by a small amount delta V. So that the pressure is also changing, right? Pressure is also changing here. So we can define the P external is equal to P internal, right? P internal plus small change in pressure, that is dP. Small change in pressure, that is equal to dP. Clear? Okay, this will be the condition for a reversible process. Now we can derive the equation for the work done during a reversible process. Generally, whenever we are considering about the reversible process, there will be infinite number of steps, right? Infinite number of steps. So we will be doing the integration part here. Here the general expression for the work is minus of P external into delta V, right? Minus of P external into delta V or dV is a change in volume will be the expression for work. So whenever we are considering the reversible process, it will be negative of integral of P external into dV starting from initial volume Vi to final volume Vf, right? So we have already discussed that for a reversible process, P external will become P internal plus dP, right? So I am writing the same term here as negative of integral Vi to Vf of P in plus dP into dV. Then whenever we are opening this bracket, right? This will be open in this bracket. It will become the same term is here, P internal into dV, then dP into dV, right? So dP, this is a small change, right? dP is a small change in pressure and dV is a small change in volume. Whenever these small changes are multiplying each other, it will become very small, right? Very small. So we are neglecting this term here. Then it will become work reversible is equal to negative of integral Vi to Vf P internal into dV. Now again we are taking the ideal case equation here. PV is equal to nRT, right? PV is equal to nRT, or pressure is equal to nRT by V, right? nRT by V. So I am taking the term here, negative integral of Vi to Vf is equal to nRT by V, right? nRT by V will be here. Then for the simplicity, I am writing like that, dV by V is equal to here, dV by V is equal to here. Then what will be the value for this particular expression? I hope everyone knows about the integration part, right? Integration part. Whenever you are doing the integration, you will take it as all these terms are constant, right? N is the number of moles, it will be constant, and R is the universal gas constant, right? R is the universal gas constant. If we are considering the particular process in isothermal condition, then temperature will also constant, right? For an isothermal process. So we can say that all these three terms are constant. So I am taking these terms outside, right? So it will become minus of nRT into integral Vi Vf is equal Vi Vf, that is equal to dV by V, right? So which means 1 by V dV. As you already know, the integral 1 by integral 1 by x dx is equal to ln x, right? Log x or natural logarithm x. So it will term as work reversible is equal to negative of nRT log V, right? nRT log V. Then we are taking the limits here. It will become, wait. We are giving the limits over here, then it will become minus of nRT ln Vf minus ln Vi, right? ln Vf minus ln Vi. So if log A minus log B, that is equal to log A by B, right? Log A by B. So it will become minus nRT into natural logarithm of Vf divided by Va. Vf divided by Va. So in order to change the natural logarithm into normal logarithm, log to the base 10, right? We will be multiplying it with the 2.303. So final, the work of reversible work, the reversible work done during an isothermal process is equal to minus of 2.303 nRT log Vf by Vi, where Vf is the final volume and Vi is the initial volume. Clear? Okay, in order to solve in the problems, you will be get the value of initial volume as well as final volume. You will put the values here. You will get the reversible work done during an isothermal expansion or compression, right? This will be the expression. Now, the next condition, that is the irreversible process. What will happen to them? What will be the expression for a work in irreversible process? Right. In the case of irreversible process, it will happen in the single step, right? It will be happening in the simple step. So we can say that it will be the general expression as work irreversible is equal to minus of P external into change in volume, where change in volume is equal to final volume Vf minus final initial volume Vi, Vf minus Vi, right? So work done by the system in an irreversible process is equal to minus of P external into delta V, right? First, we have been discussing about the reversible process. Whenever we are considering any reversible process, right, in a particular temperature or the isothermal condition, the work done is equal to the minus 2.303 nRT log Vf by Va, where Vf is the final volume and Va is the initial volume. Similarly, for an irreversible process, it will be work irreversible is equal to minus of P external into delta V, minus of P external.
check.
Okay, fine. Now we will be checking here, right? We will be checking here isothermal reversible change. So if you are taking here, Q is equal to the negative of work done, right? That is equal to nRT ln Vf by Va, or we can term that PV is equal to nRT, right? PV is equal to nRT, or P1 V1 is equal to P2 V2. So from this term you can define as P1 by P2 is equal to V2 by V1, right? P1 by P2 is equal to V2 by V1, or we can say that the same expression in terms of pressure is equal to 2.303 nRT log Pi by Pf, right? This will be the expression for the isothermal reversible change. Now we will be discussing about the adiabatic change, right? Yesterday in the previous session we have discussed about the different types of process. The one of the process, it is adiabatic process, right? In the case of adiabatic process, we can say that there will be no heat change, right? There will not be any heat change. So we can take it as Q is equal to 0, right? Q is equal to 0. So according to the first law of thermodynamics, W will be equal to delta U, right? Delta U is equal to work done during adiabatic process. Delta U is equal to work done during adiabatic process, right? So there will be one more expression to derive around the work done during adiabatic process, that is equal to N into Cv into delta T, where N is the number of moles, Cv is the heat capacity at constant volume, and delta T is the temperature change, right? T2 minus T1. Then this is the one more expression you have to be noted. It will be a long derivation, no need of that. In the JEE Main examination point of view, you will be reminding about the formula only or the expression only to solve the numerical problems, right? So work done during the adiabatic process is equal to Nr into delta T divided by 1 minus gamma, where gamma is the another term known as the Poisson's ratio. That is equal to the ratio of Cp to the Cv. Cp is the heat capacity at constant pressure and Cv is the heat capacity at the constant volume, right? Okay. Now we have been seeing about the graphical representation of work. So in the case of isobaric process, right? Isobaric process means at constant pressure, which means delta P is equal to 0, right? Delta P is equal to 0, which means that whenever we are drawing the PV diagram, right? P along the y-axis and V along the x-axis, we will be saying that pressure will be same, right? Pressure will be same. Okay, pressure will be same. This will be the diagram or the line parallel to the x-axis. That will be the graph for an isobaric process, right? Delta P is equal to 0. Then whenever we are considering about the isothermal process, we have already know there is a work done, right? Work done during isothermal process is equal to minus 2.303 nRT log V2 by V1 or Vf by Va, right? So we can draw the PV diagram as here, right? It will be here. This will be the isothermal process. As the pressure increases, volume decreases, or the inversely proportional relation between pressure as well as volume. This will be the graph for the isothermal process. That is equal to delta T is equal to 0, right? Then whenever we are discussing about the adiabatic process, there will be a particular work done, right? There will be a particular work done. So we can write it as N into Cv delta T. N into Cv delta T, where Q is equal to 0 here. So this will be the PV diagram for the adiabatic process. Then what about the isochoric process? Isochoric process. Isochoric process means there is no any volume change, right? Delta V is equal to 0 here. So we can call it as isochoric process. There will be a PV diagram, which means that whenever the pressure changes, volume will be constant, right? The graph will be a straight line which is parallel to the y-axis. Graph will be a straight line which will be parallel to the y-axis, right? This will be the diagram for the PV diagram for the 4 different thermodynamic process. First one isobaric, isothermal, adiabatic and isochoric process, right? Now we can predict the work done during a process. Work done during a process, that will be the area under the PV curve, right? Area under the PV curve. So by using this PV diagram, you can predict the order of different process, order of work done during different process as here, just like that. Work of isobaric, right? Work done during isobaric process is greater, which means area will be very high, right? PV diagram, area under this graph will be very high for the isobaric process. So isobaric process, work done during the isobaric process will be very high. Then what about this one, isothermal, right? This will be the second curve, work done during isothermal. Then adiabatic, right? Adiabatic process will be the third one. Finally isochoric process, right? Finally isochoric process. We can say that in the case of isochoric process, work done is equal to P delta V, that is equal to 0, right? Work done will be 0, that will be, the area under the curve will be 0, or we can say that work done during an isochoric process is minimum as compared to all other 3 processes, right? All other 3 processes. Okay, these are all about the work and heat energy part, right? Work and heat energy part. We have discussed about the heat. Then we will be discussing about the work done during different process. Finally, we checked about the PV diagram. By using the PV diagram, we can find out the work done during different process. And we can say that work done during an isothermal process, work done during an isobaric process will be maximum and work done during isochoric process will be minimum, right? Now here is the practice question for you. The question is that 2 liters of an ideal gas at a pressure of 10 atmosphere, expands isothermally into a vacuum, until its volume is 10 liters. How much heat is absorbed and how much work is done in this expansion? How much heat is absorbed and how much work is done in the expansion? 2 liters of an ideal gas is given here at a pressure of 10 atmosphere, right? At a pressure of 10 atmosphere. Then the condition is given that it is moving towards the vacuum, right? It is moving towards the vacuum. So we can say that here the external pressure will be 0, right? External pressure will be 0. This will be the free expansion condition, right? This will be the free expansion condition. So we can say that in the case of free expansion condition, what will be the work done? Zero, right? Work will be the 0 work done is happening during the free expansion because it is going towards the vacuum. So that we can say that generally heat will be the negative of work done. Here already work is given as 0. So heat absorbed should be 0 here, right? Heat is also absorbed should be 0. Now here is the next question about the thermodynamics part. Again, to calculate the work done, an ideal gas is allowed to expand from 1 liter to 10 liter. Initial volume is given as 1 liter and final volume is given as 10 liter. Then it is against a constant external pressure of 1 bar. External pressure of 1 bar. What will be the work done in the kilojoule? Unit should be given as kilojoule. Okay, this will be the final expression to calculate the work done. That is work done is equal to minus of P external into V2 minus V1. V2 is the final volume and V1 is the initial volume, right? So, the main important point you have to be noted that about the unit, right? You have to be calculate the work done. It should be in the kilojoule, right? So, first term you have to do that. Pressure is given in the 1 bar, right? Pressure is given into 1 bar. So, we have to be converted into the Pascal, right? 1 bar is equal to 10 raised to 5 Pascal, right? 10 raised to 5 Pascal. Then, whenever 1 Pascal is multiplying with the 1 meter cube, it will become 1 joule. So, in order to calculate this work done in the joule, we are converting this pressure into the Pascal unit as well as volume into the meter cube unit, right? So, I am taking here, this is a 10 raised to 5 Pascal, right? 1 bar is equal to 10 raised to 5 Pascal into, what is the volume here? Initial volume is 1 liter, final volume is 10 liter. So, it will take it as 10 minus 1. It is a liter, right? 1 liter can be converted into 10 to the power minus 3 meter cube. 10 to the power minus 3 meter cube. So, this will be Pascal meter cube. Then what will be the final answer here? 10 minus 1, 9, right? 9 into 5 minus 3. This will be in joule, right? 900 joule will be the final answer in joule. Now you have to convert it into the kilojoule, right? So I am taking here 900 joule divided by 1000. 10 to the power 3, right? 1000. That will be the kilojoule. Then what will be the answer here? The negative sign should be mentioned here. That is equal to minus of 0.9, right? Minus of 0.9 kilojoule, which means option D will be the correct answer. Okay, this is the final question. What will be the work done in joules when 1 mole of N2H4, that is the hydrogen, decomposes against a constant pressure of 10 atmosphere at 27 degrees centigrade? This term is based on the heat capacity, right? This term is based on the heat capacity. Based on this formula, you can give the answer to this particular question. Take it as an homework. Okay, again, the remainder about the AATS. Just enroll fast for this particular AATS. You will get the YouTube 50 of code, and then you will get a special discount of 2,999, right? So just enroll fast. Don't miss it. So that's all about from my side for today. I hope I have completed the most important topics around the work and heat done. So, just watch through the particular session. Share this particular session to your friends and family also. Do like, share and subscribe to our channel also. Till then, bye-bye all of you. Thank you so much.